My old friend Dick Feynman always used to say, after spending his life studying quantum mechanics, one of his favorite quotes was, "Nobody understands quantum mechanics." And, I think I am inching towards the point where I can say I actually understand quantum mechanics. I don't think I'm fully there yet, but I'm at least inching towards it. And I think the sort of key observation is this point about the many paths of history and the fact that we, in our experience, span those paths of history, span multiple paths of history. Just like we don't fill the whole universe, we don't span all possible paths of history, but we span a chunk of paths of history. And that's, in a sense, when we say there's, so then there's the question, okay, so that one of the issues is, why do we think that definite things happen? If there are many paths of history, why aren't we just living in a world where many different things are happening? And inside a quantum computer, I think that is what's happening. That's what a quantum computer, inside the mind of a quantum computer, it has many different things happening. The challenge with a quantum computer and the challenge of what happens in quantum mechanics is somehow you have to take those many paths of history and somehow aggregate them to something which is compatible with observers like us who believe that definite things happen. And so it's like a measuring device. It's like the molecules hitting the piston. All those molecules are doing different things, but the piston has one uniform kind of thing that it's doing. I think in the case of most kinds of quantum measurements, that it's more like a weighing balance. That is, in the case of the piston, it's just aggregating real numbers, and it's eventually, this is the average pressure type thing. In a slightly different, but very similar kind of measuring device is a weighing balance, where there are many different ways you can put grains of sand on the two sides of the balance, but in the end, it will go to thunk one direction or the other. And I think that's similar to what's happening in the measuring devices that are used for measuring things like qubits and so on, where there's sort of this binary decision about was the spin up or down or whatever else. Now, if you then ask,
talking about living with one's paradigms, another paradigm that when you're thinking about sort of the rules of quantum mechanics, and you're asking to live with is quantum mechanics. It's one thing to accept that quantum field theory is so successful.
I think the underlying rules of quantum mechanics
to accept
rather easily map onto the sort of underlying dynamics of these multi-way systems and many paths of history and so on. That stuff
there are
is
so
pretty
many
directly the
fascinating ways in which the Ruliad
The issue
connects
is,
to
can we
or
explain
derives more explicitly
why it's a
interesting
discretized
physics,
version
like
of that, which is
that
quite
of general
mathematically
relativity and
interesting,
black
blah,
holes,
blah,
like
blah.
you mentioned a little
But
bit
in the end,
earlier, but to focus
it's sort of
on one for a
unsurprising.
moment.
It's kind of just like
I'm curious about
it's an
how
actualization
living
in
with these
some
two paradigms,
sense
the
of the
Ruliad and
mechanization
quantum
of
mechanics,
things like the path of
has
the goal.
been for you.
But then in traditional quantum mechanics, it's been kind of a 100-year wimp
I'm
out,
wondering if
because
accepting the Ruliad
it's just like, and then there's this idea of measurement,
interpretation
and
of
we go from the quantum amplitudes to the measured result, and then something definite happened. And we haven't had to describe, the formalism of quantum mechanics has mathematically tiptoed around this question of how does the measurement actually happen. And in our models, there's much better chance to say, let's unpack what's inside the observer. What is the observer doing? The observer is taking all these different things that can happen, all these different threads of history, and they're equivalencing many different configurations, and they're saying, so the spin was either up or it was down. And now we get to start unpacking that and saying, well, what were the actual processes that caused that equivalencing to happen? Just like in the case of the piston with the molecules and so on, what were the processes? Well, every molecule that hits the piston causes the piston to deform a little bit. But, there are effectively sound waves in the piston that are exchanging momentum between the different places where it gets hit. And it's a rigid thing. And so pretty quickly it dissipates kind of the little deformations that come from the individual molecules. And then you have a sort of collective motion that occurs. And so similarly, and I haven't done this, and I've been wanting to do this, is to really go through the sort of the details of how different quantum measurements are made mechanically, in the lab, what you actually do. And, I know I've gone through in qualitative terms, and I think you can kind of trace that it's a bunch of equivalences that are being done. But then the question is, well, what can you say when you unpack this process of measurement? What can you then say about quantum mechanics? What additional things can you say? For example, will quantum computers work? Or is it the case that what you gain in having these many paths of history and many sort of parallel threads of computation, you'll lose but then you have to knit all these pieces together, and that takes a lot of effort. And I think that's an example of where you get to kind of make a finer statement about quantum mechanics. Now, you could ask, do we understand why the Born rule of quantum mechanics works? Not completely. We have arguments about it. We have arguments for why it should work. Have we dotted the I's and crossed the T's? Not yet. I am confident that that's going to work out. But we don't, it's just, this is one of the challenges. You have a very foundational theory, and you're trying to get it to the point where you can say, go do this experiment. I mean, there are lots of people who've said to us, we have this giant telescope. What should we look for? What actual experiment should we do to look for, let's say, dimension fluctuations in the universe as it is, or look for some other kinds of phenomena that our models predict? The problem is that actually going in and nailing down kind of, what the details of what the telescope should see are is a whole bunch of work. And it's a big stack of kind of mathematical physics and other things that you need to go through, and computational irreducibility is not your friend as far as this stuff is concerned. And, we're slowly getting there. We now have nice simulations of black hole mergers. We're starting to have simulations of quantum black holes and so on. Mm-hmm. But it's a whole bunch of work, and lots of people are getting involved in that, which is nice. But when it comes to, let's reproduce all. Okay, so I can say in terms of, I think the fundamental point about, quote, understanding quantum mechanics is this idea about broad-shield space, this idea that quantum mechanics is, so for example, the fundamental law of quantum mechanics, you could state it in different ways, but a nice way is in terms of the Feynman path integral. And the path integral says that the amplitude you get out is this, you integrate over all possible paths, and you take each path is weighted with e to the I times this quantity, the action, divided by h bar Planck's constant over 2 pi. So it's a phase, and e to the I something or other, and the something or other is this action object, which is essentially an energy density. And so the thing that's really cool is what it's saying is the phase of the quantum amplitude is determined by this energy density-like thing. So in physical space, the thing we know is that the paths particles take in physical space are deflected by the presence of gravity. Gravity, the source of gravity is energy momentum, mass, energy momentum, whatever, they're all the same thing. So in other words, a path taken in physical space that path is determined by the presence of energy momentum. It's deflected by gravity. And so now we go to the same thing in branch-shield space in this multi-way graph, and we're looking at, and what turns out to be the case is that the paths in branch-shield space basically are also deflected by the presence of energy. Energy in our models is essentially the density of updates in this network. So paths in branch-shield space are deflected by the presence of energy. And then I'm sort of skipping lots of pieces here, but basically our current belief is that position in physical space, we understand what that is. That's kind of our common experience of position in physical space. Position in branch-shield space, we're pretty sure corresponds to quantum phase. So saying that the presence of energy momentum deflects paths in branch-shield space and so on is basically saying the presence of energy momentum changes quantum phases, which is essentially what the path integral is saying. And so the belief is that what in physical space is the Einstein equations for space-time and gravity and so on, in branch-shield space It's the exact same sort of underlying process, but now it's the Feynman path integral instead. So this is, from a pure sort of elegance in physics point of view, this is quite spectacular because it means, general relativity and quantum mechanics, people have wondered how do they fit together. Well, the answer is they're the same theory, but they're the same theory played out in a slightly different space. And by the way, there are already echoes of that in what's been done in mathematical physics, the holography principles and the ADS-CFT correspondence and so on between sort of things in general relativity, things in quantum field theory. I think those are kind of echoes of the exact same phenomenon. That in some sense, these two theories are really the same theory. And for us, there's this thing we call the multi-way causal graph, which is the big graph where one projection of it is physical space, another projection is branch field space. So in a sense, this graph encodes both quantum mechanics and general relativity, and you're projecting it in different ways to get sort of the experience of different things. So let me give you one more kind of picture of sort of how quantum mechanics tries to work. So one of the things that's always confusing in quantum mechanics is things like destructive interference. So, you have two slits, you have, the photon can go through one slit or it can go through the other slit, but you say, well, it can go through either one or the other. So, by the time you're looking in the center of the screen behind these things, it's, there's got to be something there because after all, it could have gone through one slit, it could have gone through the other slit, but how can you end up with nothing there? How can you end up with destructive interference of the probability that a photon gets there? Okay, so here's what I think happens. And I think it's bizarrely similar to a phenomenon in mathematics, actually. Let me explain the phenomenon in mathematics first. So my picture of mathematics is the mathematician has a bag and they're collecting theorems that they think are true and putting them in this bag. The mathematician with a finite mind only can have a finite bag of theorems that they kind of coherently think are true. But now, imagine that you put a false theorem in there. Well, now, in sort of from the Middle Ages, people have said, material implication, if you have a false premise, you can derive everything. This is this kind of idea of, principle of explosion or whatever, that once if you assume a falsehood, then then you can derive any possible result. So what happens to the mathematician when they put a false theorem in their bag? The answer is that false theorem entails all possible theorems, and so their bag explodes, and so their mind explodes in some sense. They can't maintain all these things together. So that's kind of so now let's look at the quantum mechanics case. So now what I think happens is that the two photons, they go to slightly different places in physical space, but in branch field space, these two photons that both could end up at the center of the screen are at kind of opposite ends of branch field space. And so the observer, who is bounded in branch field space, is trying very hard to say, well, what happened? I could imagine both photons were there, but to imagine that, I would have to expand my mind in branch field space. In fact, I would probably have to expand it in some idealized way infinitely. And so just like the mathematician can't put that falsehood into their bag, so similarly, the observer of these two photons can't conclude that they just can't make consistent the picture that the photon went through either one thing or the other. And so they have to say, the photon just disappeared, so to speak. That's my, but there are lots of, all these different phenomena of quantum mechanics. You can start to have, I think, almost intuitive kinds of views of what's going on there. I think it's, to mention one from relativity that I think is very lovely. And by the way, there's an analogy in mathematics here as well. Time dilation in relativity. So, if you are an observer who's going faster, time to an observer, time appears to be progressing more slowly to an observer who's going faster. It's the phenomenon of time dilation. So in our models, you have a thing, it's represented by some sort of tangle in this network, and the thing is moving in this network. Well, the process of motion requires a certain amount of computation. You've got a thing in one place, it's got to reconstruct itself in another place. That takes a certain amount of computation. But the progression through time also takes a certain amount of computation. And the thing has a certain computation budget, so to speak, that is ultimately determined by the fundamental processing power of the universe, that's sort of the way of measuring distances in the Ruliad. And so what you end up with is you can either use your computational effort to sort of progress through time, or you can use it to rewrite your position in space. But as soon as you're rewriting your position in space, you're using up some of that budget, and so you don't get to evolve as quickly in time. And so you have to, that's why, that's sort of the mechanical reason that time dilation happens. So in the case of mathematics, well, okay, let's see. There's sort of a similar phenomenon that has to do with if you were investigating something in one theory using another theory, like
Sure.
algebra and geometry. You're trying to use algebra, but you're studying geometry, and you're kind of going back and forth between algebra and geometry. There's this translation cost that, let's see, how does this work? Basically the time dilation phenomenon comes about because as you are trying to sort of think about geometry in terms of algebra, let's say, you are necessarily incurring you're slowing down your progress in geometry because you keep on having to do this translation back and forth to algebra. And I'm not untangling all the pieces to this quite right. But that, I think there's a phenomenon there that is similar to time dilation, which is very weird. And by the way, these correspondences speak to sort of, help convince me that this picture that's sort of underneath both mathematics and physics is this same Ruliad. The fact that there are these correspondences makes that encouraging. I mean, other correspondences that what is a black hole in mathematics? A black hole, I think, is a decidable theory. So just as in physics, there can be unbounded time, so in mathematics, there can be unbounded proofs. But by the time you have a decidable theory, the proofs are going to be bounded. And so that's like a decidable theory is like a black hole. And then you have in physical space, you have all these singularity theorems that say when you have too high a density of energy momentum, you inevitably form a black hole. In mathematics, the statement would be when you have too high a density of proofs, you inevitably end up with a decidable theory. And so this leads to very bizarre things. Like, for example, the future of the universe may consist of a bunch of black holes. The future of mathematics may consist of a bunch of decidable theories. And in other words, that the sort of inexorable future of the universe sort of is similar to the future of mathematics, so to speak. Another thing, correspondence between mathematics and physics, is homogeneity in the physical world. That is, that we can move around, we believe that physics is kind of the same here as it is in the Andromeda Galaxy. In mathematics, the statement would be mathematics is kind of the same in the algebra place as it is in the geometry place. So in other words, there is an inevitable translation from one field of mathematics to another. If the mathematical universe is reasonably homogeneous, which I think I can argue that it is, then it is necessarily the case that there will be these correspondences between these very different areas of mathematics. And we see some evidence of this, of all these kind of dualities between different areas of mathematics and so on. But it's sort of interesting to see that homogeneity in physical space, the analogy to that is the presence of these things. And I think, by the way, in a recent thing that I've sort of come to imagine is that category theory, for example, which is one example of a kind of a broad sort of structural sort of description of lots of areas of mathematics. Category theory is a characterization of a so one feature of category theory is you say, oh, we apply this morphism, then we apply this morphism, and category theory says if you can apply this morphism, then that morphism, then there's always a morphism that just jumps all the way. That's just an axiom of category theory. That axiom kind of denies computational irreducibility, because if each of those morphisms was a computationally irreducible step, then to say, oh, but there's just a supermorphism that jumps all the way, is to kind of say, but that there shouldn't be that supermorphism if you had to go through all these computationally irreducible steps. And so I think that that's in a sense, category theory is a description of computationally reducible, is some kind of meta description of computationally reducible pieces of mathematics. But it's one of these things that I think is somehow there's a correspondence between that and this thinking about sort of homogeneity in mathematical space.